So today we have Alex talking to us about, let's see, is it going to be Turing machine stuff or just computer science in general?
So I can hear myself in the background.
Oh no. Maybe if I turn mine down.
My audio is off.
Yours is off. Okay. Try again.
Okay. I can still hear myself, but it's not as bad. So I have a recap of Turing machines, and then I'm talking about computation. So a little bit of both.
Okay. Yeah. Sounds good. So take it away whenever you're ready.
All right. So yeah, let's start with the recap. So I just sort of wanted to bring up that there are kind of like two basic ideas of like abstract modeling for computation. There's state machines, which were, famously talked about by Alan Turing, and then lambda calculus, which was created by his mentor, Alonzo Church. And together they wrote the solution to the Anschuldigung problem in 1936. And Alan Turing is most famously known for the Turing machine, which is a state machine. So we're going to focus on those. So there are several classes of automata. One of the main limitations of a state machine is that its memory is restricted to the number of states it has. And this is kind of important when we think about like computational complexity and that kind of stuff. So here I've just formally defined what a Turing machine is in English. It's the best analog we have in terms of state machines to what a modern computer is. So it's an idealized state machine that is somewhat similar to a finite state machine, but it is important in that the memory is infinite, and the memory is defined as the tape, which is divided into discrete cells. And a Turing machine, unlike a state machine, can both read and write to this memory. And it can move forwards and backwards in the tape or the memory. And anything it does basically happens immediately. There's no sort of like pause that happens. So that's kind of the idea. And Turing machines are really cool and really interesting in that they, despite their simplicity, capture the entirety of algorithmic computation. So like anything that you can describe in an algorithm can be placed in a Turing machine or described by it. And the really cool thing is, up until then, algorithms were sort of this like hand wavy thing that they were talked about. But Turing machines and Alan Turing's paper allows algorithms and allows us to talk about them, to study them rigorously. And interestingly enough, quantum computers also follow the Church-Turing thesis, but they do so in a different way that I'll talk about later. So here I'm mathematically defining a Turing machine as a 7-tuple, where Q is a finite set of states. Sigma is the input alphabet, which I'll talk about formal language later. And then, so gamma is the tape alphabet, which is a superset of the sigma alphabet. And it contains something called the blank symbol, which is basically the way that a Turing machine will clear its memory. And then delta is the transition function, and the transition function is the special thing about Turing machines. And then you have the start, accept, and reject states. And so I went ahead, and I didn't expect anyone to do this, like in Roy's presentation, because I think we would be here all day. But I sort of went through one of the exercises in the book and completed it, so you can kind of see what it looks like. So this one just takes a binary number as some arbitrary binary number as input and outputs the bits of X in some reverse order. So I don't know if anyone wants to sort of take a stab at it, but I sort of mentioned language before, and so I was talking about sigma. So like, what do you expect the language of this Turing machine to be?
Okay.
I mean, so the characters in your alphabet can only be like zeros and ones.
Yeah.
And so I guess your alphabet is just composed of words made of binary numbers.
Yeah. So like if you were to talk about your alphabet being like 0 would be the first letter and 1 would be the second letter, and then that would be the set of 0 and 1, sort of. So I went ahead and made the Turing machine, and so this is sort of like an idea of what it would look like, and so and then I defined it at the bottom. So you have the input language, as you said, is 0 and 1, and I represented the blank symbol as B. And so I'm not going to really walk through all of this because it's like tedious, but basically what's happening is you have a set of some arbitrary length of the language within defined within sigma, and you're saying you're going from the number, so you're going from Q1 and then you're going to copy that over to the length of that string -1, and then you're going to do that in reverse order, and that's just like a sort of a state machine representation of that. So that's sort of the recap of what
Sorry,
Turing machines are.
Alex, could you just go back one slide?
Yeah.
Yeah. So, like, if you just explain what any one of the arrows, the notation of any arrow means, that will make a lot of sense.
Sure. So so this is the beginning state, and this is the accept state. And so you're sort of traveling in here. And so basically, anytime this state receives a 0 or a 1.
If you're pointing at something, we can't.
This is so sad. Hold on. Let me see if I can.
There's a laser pointer on like the slide thing, so that you can. Oh my god! I don't know what that is.
Oh.
But...
No.
Spilled water on the paper.
I'm suffering. I don't know what's going
It's
on.
all censored now. Nothing signed the release.
Oh god. This is what I get for trying to annotate. Oh god. How do I undo it?
Pause the recording.
Yeah, let me pause really quick.
Hell.
I know.
Okay, so after the announcements, okay, so basically Q1, so if you go from Q1 and you go down, you can sort of see that for any time you input, if you go right and input a 0, you'll end up in Q2. And so basically what the arrows that come back into each state are is that if you were to input that letter in the alphabet, you would remain in that state. So for instance, in Q1, if you were to remain in, let's talk about Q4. Q4, if you were to input a 0 going left or a 1 going right, also going left, then you would remain in the state Q4. So you could only do you could only go out of it. I forgot.
Okay, let me try to crack, because this is one of the first Turing machines I ever worked out by hand, so I remember it very well.
Yeah.
So the idea is that you have a long tape, right? And you have any number, some number in binary. So you have 0, 0, 1, 0, 1, 0, blah 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 blah. And then after that you have B B B B B B B. It's just blanks, everything after that. So the idea is that what this machine does, if you look at Q0, which is your initial state, so the first symbol says 0/0, R, which means if your tape has a 0, which is the first 0, you write back 0 in that, basically do nothing, and move 1 to the right. And similarly, 1, 1, R means if it's a 1, do nothing and move to the right. So the first, you stay in state Q0 till you reach a blank. So basically you reach the end of your binary representation of your number. Once you reach a blank, you write in blank and move 1 to the left. So you're at the last digit at this point of your number. And so the Q1 basically does the same thing. If you see X, write x, move to the left, keep doing that. And why you have to split it into Q3 and Q2 is if you get a 0, move all the way to the end, write a 0, move all the way back. That's through Q2. If you get a 1, move all the way to the right, write a 1, move all the way to the left. That's through Q3. So this is basically like the A slash B comma C is if you see alphabet A, write alphabet B, move left or right. And that's the way this notation works. And so once this whole process is done, it's basically Q1 splits into Q2 and Q3 because your alphabet only has zeros or ones. So if we add more alphabets, you will have to do one more split and then come back to Q1. So going back. Yeah.
All right. Thank you. That was much more concise than I would have made it. All right. So anyone have any questions about that?
Yes. Can you go back to the definition of the Turing machine?
Yeah.
So right here you say it's a 7 tuple, but then when you give an example, I can't really tell. It seems like there's way more than 7 elements.
Yeah. So within sigma and gamma are both sets.
Oh, so were there just no brackets or something?
Maybe they didn't show up. I wrote this in LaTeX like 30 minutes, or not 30 minutes, like 3 hours before I was presenting. So I'm sure my LaTeX is just messed up. But yes, there are supposed to be brackets.
Yeah, you need a slash in front in order for that to show up.
Yeah, there you go. That's probably what it was. So sorry about that.
Oh, thanks.
Yeah. That's what it is. Because imagine that there are, I can't draw on the screen, but imagine there are brackets around 0, the first 0, 1, and then the second 0, 1, X and B. Those are also brackets. Yeah. Overleaf failed me.
As it does.
All right. So some of the questions that were postulated in Nielsen and Schwang were why do we care particularly about computational analysis? And so he kind of split it up into, or they kind of split it up into like, what is a computational problem? Why or how do we want to design algorithms to solve these problems? And one of the main ones is, what are the least amount of resources that we can use to solve a given problem? And these questions are actually sort of extremely important, and they make up a whole section of theoretical computer science, and it's complexity analysis, basically. So I'll just sort of explain basically what one of the main ways we use to define like algorithms. So computational resources are often described in what's called big O notation. There's also big omega and big theta, but I think that big O is kind of the most ubiquitous, and also the one that we kind of want to look at here in terms of like why we're using quantum computing instead of classical computing, besides the fact that it's cool. So big O notation is sort of to set up the upper bounds of the behavior of what a function may do. So basically, if you're looking at an algorithm, you want to see sort of like where the upper bound of that algorithm will end up being. And you'll usually use this to see the worst case scenario of an algorithm. And this is usually for time complexity, but you could also use it for space complexity as well. So you're looking at some sort of algorithm, and say you're going through an array of numbers. Will it take the entire array to finish whatever you're doing, or will it only look up one specific instance in the array and be done? And so these kinds of things don't really necessarily matter in small numbers, but when you apply an algorithm to a large set of numbers, a large set of n, suddenly, something that may have been very fast for, n cubed is for 2 or 3 numbers suddenly becomes, 10 hours, or the heat death of the universe at n equals 10. So I've included a big O graph to sort of go through it. So basically, order 1 is like, it just happens immediately. It's and so these are defined basically by the biggest number of complexity. So basically, like, an order 1 operation may take 10 million times, but it only has to do it independently of the number of runs the algorithm may have to do. So for instance, if you have like a for loop or something and it runs 10 million times, but that's independent of the data it's being fed, then it's still order 1 in terms of the data, or in terms of the complexity of the data, rather than the complexity of running through the actual data, if that makes sense. I guess a for loop would be a bad example. I just, like, you have a program and there's like 10 million instructions that it has to do. It's still order 1 for each one. They don't have any additional complexity. That's a better example. So as you can see, as you go up, obviously the things that are below linear time maintain, and this one doesn't have, there's also one that's called n log n. But the things that are below linear time run way faster, and then suddenly you start to hit things that are order n squared or n cubed, and then you start looking at things that suddenly you have 10 points of data, and then they take forever. So for example, like the Fibonacci problem, that gets extremely difficult to compute, or extremely long once you hit large numbers, like, or not even large numbers. Once you hit like 15, it becomes extremely difficult to compute. So computational complexity sort of, in a broad sense, splits up these two sort of ideas of things that are relatively reasonable to compute and things that are unreasonable to compute into problems that can be solved in polynomial time versus problems that can't. So if you look at this graph, you could also have one that goes up even further, that's 2 to the n. And so that's exponential time versus polynomial time. And so you sort of see, okay, how long does it take to make this decision? And is it worth necessarily, or not, is it worth, but how long will I have to wait for, 10 or 12 points of data? So I don't know why I put this here. I should have put it earlier, but this is formal language theorem. And I sort of put it here because Nielsen and Schwang talked about it here in the computational complexity section, but I think it would have been better to be put earlier. And they sort of mentioned that lots of computational problems within P and NP sort of decision space are decision problems. And so you're sort of looking at, a yes or no question, but something that may take a lot of computation in order to figure out whether it's yes or no. And so they're often about languages, and so they talk about the formal language theory. I feel like this was probably better to, like I said, be put earlier, but that's where they put it in the book. So, and so I sort of found the definitions of P and NP, and I'm not really going to go into that actually. That's nobody's business. And so one thing that I do want to go into is that I think I have it here. So not only are there things that are NP, which are very difficult to solve, there are also things that are NP complete, which are, as far as we know, if you are in the highly debated P does not equal NP camp, they are even more difficult to solve than NP problems. So there's this, I stole this off of Wikipedia, but basically, if you're in the camp in which you believe that at some point in time we may find a polynomial, or at some point in time we may find the ability to describe NP problems as P problems, then even then they're only approximately similar to P and NP. So I think that's kind of interesting. So an example of that is, or maybe not an example of NP complete, but I'll talk about some really famous NP problems. So like the traveling salesman problem, where you basically have some arbitrary graph of n nodes and you want to find the best path to go to every single one of them. That's an extremely difficult problem that is like very relevant to us. And so that's kind of where quantum computing comes in, is that you have all of these difficult problems. I think actually like maybe a third of Nielsen and Strong at the end was just showing different problems that were NP that could be, that were like, that they talked about. So I think that's kind of interesting. Actually, let me go ahead and pull that up, because I think that some of them are pretty interesting. Like I gotta, so like, let's see. Where are they? Yeah, so like the 0-1 integer programming, and lots of things actually to do with matrices often become NP because you have the space complexity of a matrix. And lots of issues with graph theory as well. And so you may have some arbitrary n nodes, and it takes an extremely long time to find some sort of path between those nodes. So all right, that's all I got. Any questions?
Yeah. So I was under the impression that linear programming was actually easier on a computer, but apparently this is saying that it's not.
Is it only easier if it's not restricted to integers?
Oh.
So yeah, you're muted.
Yeah, if you restrict to integers, it's a tough problem. But if you do a rational relaxation, I think that's what it's called. I think you allow your solutions to be rational numbers, then you can actually do like interpolation and stuff like that, and that makes the problem easy to solve.
Wow, that's really interesting.
So I had a question on slide 17.
All right, let me take a look at that slide. Oh, my Wikipedia
Yes.
image.
Well, it was honestly more of just a comment, and just to say, like, so on the left hand side, we assume the problems that are good for quantum computing, they're in that sliver right between P and NP complete. Is there any reason to do, like, there's no reason to do a algorithm in P on a quantum computer, right?
I mean, you can. Maybe they'll make it faster, but like at the point in which we have computers now, not really. It's more about like a proof of concept than.
Yeah, Margaret. So technically, searching through a list is in P, right? because you just go through every element of the list, and that's order n. So that's polynomial, so that's in P. But Grover search algorithm is in square root of n. So it still makes sense if you, even within P, if you can speed it up, then it's still a good idea to do it, right?
Okay, so that kind of falls into the, if the right-hand side is correct, there's still an advantage to having quantum computers. Because I was always under the impression that if P is equal to NP, then we should all just stop. Because everything is kind but
I mean,
there's still advantages.
Yeah, definitely not. Because obviously, even within P, there are still things that are very hard to compute. They're just within P. You know, like
n power 100 is technically in P, and it's just really bad. So
exactly.
you would rather, you should still think about if you can speed it up.
Because like you can have something be in P and still take like 6 months to compute for 5 on a regular computer, but then like, you know, if you have a quantum computer and it takes, you know, rather than 6 months, it takes 2 weeks. It's like, yeah, that's a significant improvement. I would want to do that. So, and I think about like, in particular, maybe like things that take a long time, like you would want to do them on a quantum computer, maybe not even for the sake of like I said, not even maybe for speeding them up. Like, let's say you want to do like binary search or something, and you know that that's really fast, but it's also like a proof of concept. So I wouldn't say that if P equals MP, you shouldn't do quantum computing, because I think that's that would be sad.
Yeah, yeah. You know, we like that job security.
Exactly.
I know you said you were gonna skip it, but could you go over the P and MP? Or
it's just sort of like further, like more mathematically describing why, or not why, but how a Turing machine will run on polynomial time for all inputs.
So I think an important distinction is that NP does not stand for non-polynomial, right? Like it stands for like non-deterministic polynomial.
Yeah.
Can you like say something about that? Or because I think that's what this list is saying. Basically, you have like an oracle, right?
Yeah, so basically NP is where the decision problem, they have a proof verifiable in polynomial time. So if you can prove them in polynomial time, that they reside in NP. So it's not necessarily, they're not. So yeah, that's where the non-deterministic polynomial time comes in. So they're not necessarily non-polynomial, like you said. Yeah.
All right. Any other questions? All right, let me stop the recording.